Your generic right-tailed test, say, for a population mean looks like this. You got a null hypothesis. Haven't done any hypothesis testing yet this semester, but you've done it before. Null hypothesis is typically written mu equals something. Technically speaking, you should write the alternative hypothesis first. Really, that's your research hypothesis. And if it's a right-tailed test, it's typically that mu is, well, for right-tailed test, it's that mu is bigger than some number, mu sub 0, say. Technically speaking, you could argue that the null hypothesis is the complement of that. If the alternative is that mu is bigger than mu 0, then the null would be that mu is less than or equal to mu 0. However, we almost always keep the null hypothesis as a simple hypothesis, mu equals the null value, mu 0. Maybe I'll write technically. Mu is less than or equal to mu 0, but we almost always write it as a simple hypothesis, the equality using an equal sign makes this a simple hypothesis. And that's good enough. For reasons I'll get into, to consider the null hypothesis to be a simple one. Effectively, whatever you want to do is good enough in that case. We will actually consider situations, unlike what we did in problem stats here in these coming days, where the alternative hypothesis is not a simple, a simple hypothesis instead of a non-simple composite one like this. But this is what we mostly did back in problem stats, is this kind of test. And remember what we did. There were two approaches. One approach was to find something called the p-value of the test. That's called significance testing. And remember in general what the p-value was. I'll just describe it in words. I'm not going to write those words down. Just to remind you, it's the probability of obtaining an observed value of a certain test statistic, like X bar, or like Z if you convert to standard normal, as extreme or more extreme as what you actually observe from your data, under the assumption that the null hypothesis is true. So you're giving the null the benefit of the doubt. You're assuming it's true. What is that probability? If it's low, if you have observed something rare when the null is true, then you say, well, that means I think the null is false, so I reject it. Reject the null in favor of the alternative. Accept the alternative. You think the alternative is true. But you might make a mistake when you do that. The null hypothesis might really be true, and you have observed something rare when the null is true. So you might make what's called a type 1 error, rejecting the null when it's true. On the other hand, if the p-value is not very small, how small is very small? You know, the typical standard was like 5%, but that's not set in stone. If the p-value is not very small, for sure, like if it's 30, 40%, don't reject the null. You don't have sufficient evidence to reject the null. It's not that you necessarily think the null is right, but you don't have sufficient evidence to reject it. So you either say we do not reject it, or you say, okay, I accept the null. But even there could be a mistake. You could be accepting the null when it's false. You could be making a type 2 error. Remember these things? Let's think about these things again, but now in the context of also including a level of significance. The letter alpha in this context is called the level of significance of the test. And if you do the test with the other method, instead of finding p-value, the p-value, you find what's called the critical region, rejection region. Alpha helps you figure out what the rejection region is. Because what alpha really represents is the probability of type 1 error. Rejecting H0 when H0, the null, is true. In a courtroom, the null is innocent, the alternative is guilty. While you go through the trial, you give the null the benefit of the doubt. That's the assumption of innocence until proven guilty. A type 1 error then is like convicting an innocent person. As a society, we typically think of convicting an innocent person as a worse mistake than acquitting a guilty person. I mean, they're both bad, but we as a society, and I think most societies generally think convicting an innocent person is worse. A worse mistake. And sort of that's sort of the philosophy behind a type 1, calling this a type 1 error, and the other kind of error, a type 2 error, is like rejecting the null when it's true is sort of considered to be worse, a worse mistake, a worse decision. It's not a math mistake, by the way, it's a mistake in your decision when you make such a decision to reject the null when it's true. Of course, in many situations, you don't really know for sure whether the null is true. That's why you're doing the test. But even after you're done with the test, you still don't know for sure whether the null is true. You just have evidence against it. You have strength of evidence against it. Is it strong evidence or not so strong? Let's think about this graphically. So I'm not doing calculations here. I'm more focused on concepts. Not sure if we'll have time for calculations or not. We'll see here. What I want to draw, I want to make some graphs. I want to draw, first of all, a number line. On this number line, draw a point. This point is going to represent the null value, mu sub 0. Right, that's the null value. It's a particular number. Could be 10, could be 20, could be 37.2. Remember, X bar is an unbiased estimator for mu. We also have the central limit theorem that says that X bar is approximately normal when n is large, even if the population is not normal. Although some extra special theorems apply that actually that X bar is exactly normal, not just approximately normal, but exactly normal when your population is normal. That was something sometimes called the Cornerstone Theorem in chapter 7, before the central limit theorem. This Dr. Wetzel and I have called the Cornerstone Theorem. It's important, though when you apply it in real life, it's always sort of applied approximately. If you got a random sample of size n from an exactly normal distribution with mean, mu, and variance sigma squared, then X bar, the sample mean, is exactly normally distributed with mean, mu, and variance sigma squared over n. This is a theorem that can be proved if you're assuming you are sampling from an exactly normal distribution. When you apply the theorem, though, in real life, you might argue that it never applies exactly, because how can you ever know for sure that you have an exactly normal distribution? No doubts about it. So it's really more of an approximate application of a theorem in real life. Sounds funny, but that's really what's going on. It's got mean mu. That's true no matter what, as long as you're doing random sampling, whether the background distribution is normal or not, because X bar is always unbiased. And in fact, the variance always equals sigma squared over n in general. The new thing is that it's normally distributed. So I want to draw a normal distribution here. And what is this normal distribution supposed to represent? It's centered at mu0. It's supposed to represent the distribution of X bar. Often not just called the distribution of X bar, but for emphasis called the sampling distribution. I'll put the word sampling in there with, say, in parentheses, sampling distribution of X bar. Some of you know from helping out in math lab, then statistical analysis, we usually do call it the sampling distribution to emphasize that it comes from a random sample. X bar is a statistic. It's computed from a random sample. So certainly we can just call it the distribution of X bar, but for emphasis, for conceptual educational emphasis, we call it the sampling distribution. And it's not just for education's sake. People out in the work world will call it a sampling distribution as well, because that's what they were taught. Most people, even who use statistics, are not taught statistics at this level. They're more taught like a business stats course, and their teachers use the word sampling distribution back there. X bar is unbiased. This is the same as the mean of X bar. And the standard deviation of this sampling distribution, which looks exactly normal if this population is normal and approximately normal, even if the population is not normal, is this horizontal distance between the vertical line there and this inflection point. And that distance will be the variance of X bar, or the standard deviation of X bar, excuse me, sigma sub X bar. And that'll be the square root of the variance of X bar, the square root of sigma squared over n, which simplifies to sigma over square root of n. And when you decide on the level of significance for a test, what you're really doing is you are defining something called a rejection region or critical region. Both names are used. Critical region is sort of the more general name. People use the word rejection region to emphasize we're using it for deciding when to reject the null hypothesis. And for a right-tailed test, it's going to be a region to the right of some number, some critical number. What should I call it here? How about X sub alpha? Okay, that's an X, it's not a chi. My cursive X's look like chi sometimes. But X sub alpha, the area to the right of that is alpha. And that is the probability of a type 1 error, because this is going to be the rejection region. The values of X along the number line to the right of X sub alpha are going to be the values of X that lead to rejecting the null. So we call it a rejection region. We also call it a critical region because it is critical for solving the problem, you might say. And the boundary point there is sometimes called the critical point or critical number or critical value. Rejection region or critical region. If we get an observed value of X bar based on a random sample of numbers, talking data here, in this region greater than or equal to X sub alpha, which some books call X sub crit for critical point, then we will reject the null hypothesis. And if we don't, then we fail to reject. the null, we can say accept the null. Remember doing that? These ideas? Standardization, converting to Z, means we can also think about these ideas in the context of a standard normal distribution. We can also draw a corresponding standard normal curve N01 centered at 0, and the critical point is going to correspond to Z sub alpha, which, you know, if you only have the table, you can look up in the table. That area equals alpha, and this is the rejection region or critical region in terms of Z. You can think of it either way. And how do you convert to Z here? As always, take your variable or your data value, your observed value of X bar, I should say, if you have data. Subtract the mean of the distribution, which is assumed in the null hypothesis, and divide by the standard deviation of the distribution. The formula connecting these in the random variable form is capital Z equals capital X bar minus mu sub 0 over sigma over square root of n. Right, you've done these calculations before. I probably will assign a few problems where you have to calculate these things. It's easiest to figure out the rejection region in terms of Z first. And therefore, it's typically easiest to do this first and decide whether to reject or not based on the value of Z. This is your test statistic for the test. I mean, you could call X bar a test statistic as well. But the test statistic we typically talk about using is after you convert it to Z. When we think about the rejection region in terms of Z. So for example, if alpha is 0.05, Z sub alpha is Z sub 0.05, that should be 1.645 if memory is serving me correct. Let's use technology. Inv norm, right? We're after effectively percentiles here. We're after the 95th percentile there. 0.95, mu is 0, sigma is 1. Yeah, about 1.645, I guess, right. It rounds closer to 1.64. If you use the table, you see you typically either round to 1.64 or 1.65. But if you want 3 decimal places of accuracy, 1.645 is what to use there. So if alpha is 0.05, if it's a 5% level of significance for a right-tailed test, you'd reject the null if the observed value of the test statistic is greater than 1.645. And you'd fail to reject if it's less. What if it equals? It's up to you, I guess, if it equals it. I guess I would say as a default, go ahead and reject it. I mean, if it's close to the boundary, it's not really clear cut one way or the other, and maybe it doesn't make a big difference one way or the other, but yeah, reject the null if the observed value of Z is greater than or equal to 1.645, fail to reject if it's not. I think with our remaining few minutes here, I still don't want to do an example, but you should be able to for your homework. Instead, I want to talk about type 2 errors, probability of a type 2 error, and a power of the test here in just a few minutes. A type 2 error is when you fail to reject the null when you should have, because the alternative is true, meaning you failed to convict that guilty person. Beta is the probability of a type 2 error. Fail to reject H0 when H0 is true, or excuse me, is false. H1 is true. Another important quantity is called the power of the test. It's 1 minus beta. It's the probability of doing what you want to do as a prosecuting attorney. If that person's really guilty, you definitely want to be able to convict them. Do you have power to convict them? Probability of rejecting H0 correctly when H1 is true. Doing the opposite thing. You're not making a type 2 error there, you're doing the opposite thing. That's supposed to be in H1. Ignore that dot there. As these things are stated, they're not well defined. Because what does it mean that H1 is true? It's not a simple hypothesis. There's lots of different things that mu could be if H1 is true. Infinitely many numbers, in fact. So these are not well defined. So to compute them, you have to decide on a value of H1, which brings up a practical question of how to decide, which we won't talk about today. In just 1 or 2 minutes here, instead, we will just focus on the picture again. So here again is the sampling distribution of X bar if the null is true. But if the alternative is true, that's not the sampling distribution of X bar. If the alternative is true, if mu equals, say, mu1, that alternative is true, then the sampling distribution of X bar looks more like this, centered on mu1 instead of mu0. The rejection region is still the same. There is still some value X crit or X sub alpha, I'll call it X crit, where you reject in the null based on this area under the green curve being alpha. That's still the same, because you still have the same null hypothesis. Making a type 2 error, failing to reject the null when it's false, so you should have rejected it, means you were not in the rejection region. X bar was less than X crit. But if this alternative is true, if mu equals mu1, then the probability of that happening is going to be this area under the red curve to the left of X crit. That area equals beta. And therefore, this area over here under the red curve is the power. And the goal is to make both alpha and beta small, or said another way, make alpha small and the power big. How do you attain that goal? One way to attain it is make mu1 further away from mu0. But is that right? Is that best? Another way is keep mu1 where it is, but maybe make the sample sizes n bigger, which makes these curves skinnier. Though that does affect what the rejection region is, so you have to recompute the rejection region. We'll get into some computational details on Thursday before we keep moving toward the Neyman-Pearson lemma. Have a good day.